Yeah, that's deleting qubits. Now we're going to talk about adding qubits, by which I mean like adding them into the system. So I'm not actually going to teach you any new laws of quantum here. Like everything I talk about today, you already know these rules of how state manipulation works and newing qubits works. But I'm going to introduce some new notation that we're going to start using somewhat because it makes our lives easier. So new topic, newing qubits. So let's suppose that a person called Alice creates a qubit A in her lab and gets it into a certain state. State, oh boy. R amplitude on 0 and S amplitude on 1. Okay, and let's also suppose that a character called Bob also creates a qubit called B in his lab and gets it into the state X amplitude on 0 plus Y amplitude on 1. Okay, so we can also write this as a little 2D vector like this. Okay, you might be thinking like, oh man, like this guy again, he's always like introducing these like funny like characters or names like Alice and Bob. Like that doesn't sound very formal, but like actually quantum computing people are like always like the most serious people are always talking about like Alice and Bob. And Alice usually like owns like qubits that like start with the letter A, and like Bob owns or creates qubits that start with the letter B. And I don't know how they got these particular names. But it's actually really helpful to introduce these people as like characters because we are going to see that it's very important to consider, and we'll consider it in today's lecture, like qubits divided into two groups, like maybe the A qubits and the B qubits, and to try to think about like how do they depend on each other and are they entangled with each other? We'll talk about that later in this lecture. And it is good to imagine like there's people involved in the story. So we imagine that like maybe they just made these qubits separately in different rooms, but now they're going to bring them together because they want to do some joint 2-qubit instruction on them, like maybe if A, then toggle B. And if you're going to do some joint instruction on A and B, you need to know their joint state. So what is the joint state, one might ask, of A and B? Okay, so let's think about this. And there's not a great mystery. I mean, like we know, this is really just, a couple of new qubit operations and some couple of unitaries to prepare these two qubit states. So we know how to figure it out. But I want to say that whatever it is going to be, we're going to notate it in a special way. We'll notate it, or we'll see that it can be notated as this. So R amplitude on 0 plus S amplitude on 1. That's Alice's qubit state. Okay, then this like circle times, and then X amplitude on 0 and Y amplitude on 1. So this symbol, \O times in LaTeX, it's pronounced tensor product, or tensor for short. And we'll see this is just a representation of the 4-dimensional vector, or the 4 amplitudes corresponding to the joint state of A and B. Okay, so let's figure it out now. It's not very complicated. I told you this physical story, but like we should always just fall back on, the code, if you will. So we can like say, like Alice did, new qubit A, and then some 1-qubit unitary is probably like, you know, a rotation or maybe a reflection, U, with the property that like U, when you apply it to 0, which is the starting state for A, is what I said, R amplitude on 0 plus S amplitude on 1. And we'll similarly assume Bob did a similar thing. You know, Bob also made a new qubit called B, and then applied some unitary, I'll say V, probably some other rotation or reflection that had that took his qubit to x0 plus y1. Okay. In other words, like we can just view the whole story as, you know, 1 new qubit A, 2, do the instruction U on A, 3, new qubit B, and 4, you know, instruction V on B. Okay, and then this is the sort of thing that we could analyze like way back in lecture, I don't know, 4 or something. You know, so if you just do this code, what is the new joint state of A and B? So let's figure it out. We got our amplitude trees, and we'll skip forward a little in the amplitude trees. So like after line 3, yeah, so after line 2, obviously we have 1 qubit and its state is this. And then we do new qubit B, which just like sticks a B into the second coordinate. So it's kind of like, you know, we got to this state, R0, 0 plus S 1, 0. We're like in sort of amplitude tree world, it's like dot, dot, dot. And we got with amplitude R, we got to 0, 0. And with amplitude S, we got to 1, 0. And you know, remember, this is the A qubit, this is the B qubit, A qubit, B qubit. Okay, and then we do line 4, which is like V on B. Okay, so this branches X, Y, X, Y. Yeah, and here, I mean, like B is 0 here, so we know that V takes 0 to X, 0, Y1. So it's just like with probably X, we get to 0, 0, and 0, 1. And over here, A is 1, that's fine, and B is still 0. That's why we get to 1, 0, and 1, 1. Okay, so the new final state, it's like the product of the amplitude. So we get like Rx on 0, 0, and we get Ry on 0, 1, and we got Sx on 1, 0, and we got Sy on 1, 1. Okay, that's the new state. And that's the joint state of A and B. So we can now just say, by definition, by this, I mean star this. Okay, so this is just going to be another way of writing that expression over there. Or we want to use vector notation. What I'm saying here is that this little 2D vector, RS, that's a 1 qubit state vector, tensor product, this other 2D state vector, XY, equals this tall state. It's a 4-dimensional vector, Rx, Ry, Sx, Sy. Okay, so this tensor product symbol is actually some kind of vector multiplication. In fact, as you'll see on the homework, it's actually some kind of matrix multiplication. Not the usual matrix multiplication, but like a different multiplication-like rule that you can do on matrices. Today in class, I'm only going to talk about this rule in the context where these matrices happen to be vectors. Yeah, and really, maybe as you'll see in the homework, this is really like you take this vector and like you put a copy of it in every entry here and then multiply. So this is kind of like r times xy, s times xy, and then you remove like extraneous parentheses. Other way to say this same thing is with these like cube diagrams we were drawing so much. Like we might call this RS, 0, 1. It's like a little one-dimensional cube diagram. We do tensor product, a horizontal one, x, y. We should get like a square diagram. And we do. We get like Rx, Ry, Sx, Sy. So 0, 0, 0, 1, 1, 0, 1, 1. Okay, so these are all like saying the same thing. So I'm going to tell you some facts about like algebraic facts about this tensor product symbol. And again, I'm not going to like tell you every fact or like prove in detail every fact. I'll leave some of this to homework, but it's pretty intuitive. So I just don't want to take like forever. I mean, the summary is this symbol behaves like non-commutative multiplication. By which I basically mean like if you kind of pretend like it's multiplication and like in this context and apply a few additional rules, then it all works out. So I can add non-commutative means that like well, it means that if you do U tensor product V, it's not necessarily the same thing as like V tensor U. So just like with matrix multiplication in general, you can't just like swap things. You have to remember the order. But it is, I'm being a little precise here, but imprecise, but I hope you'll get the gist. It is commutative sort of vis-a-vis scalars. I'll do an example to explain what I mean. And it also like distributes across addition as you expect a good multiplication should. Okay, so let me illustrate this. So I'll start from here. Happy face. And I'll just FOIL it. You know FOIL, right? From like high school or maybe middle school. This is like expanding a binomial product. First outside, inside, last. So we can just like expand this out, thinking of this as times. And we kind of get like, okay, R tensor product 0 times, or sorry, R0 tensor product X0 plus, okay, then outside we get like R0 tensor product Y1 plus the inside, that's like S1 tensor product X0 plus the last is like S0 plus, tensor product Y1. Okay, that's legit. And now, when I say like, that's kind of using this rule. When I say it's like commutative vis-a-vis scalars, it means that like these scalars, like R and X, these are just numbers. You can like, I don't know, pull them out of every thing and like group them together. So what I mean is like, this is Rx times 0 tensor 0 plus Ry times 0 tensor 1 plus Sx times 1 tensor 0 plus sy times 0 tensor 1. And if you don't believe me, you can like just look at the definition of what this is and verify that everything I'm writing is true, but you can also take my word for it. Okay. And now there's like a very happy and enjoyable notational felicity that arises here. Like, let's take, for example, this expression, 1 tensor 0. Okay. And like the meaning of this is like, the meaning of this is the joint state of qubits A and B. If Alice just sat in her lab and made ket 1, and Bob sat in his lab and like made ket 0, and then we brought them together. And we really know like this should just be like 1, 0. Like that's kind of what it meant, right? Like it's this basic state where the first qubit is 1, the second qubit is 0. And this is true. I mean, by this true fact up here, this is really saying, well, ket 1 is 0, 1, and ket 0 is 1, 0. And if you plug that into the formula up there, you get like 0, 0, 1, 0. And this is indeed like our notation for 1, 0. I know there's like a lot of 1s and 0s here in like weird places, but hopefully you buy it. And that's true in general, like, I don't know, like 0 tensor 0 just means it's the same thing as 0, 0, and so forth. So this is like Rx, that's a number, times the vector 0, 0, that's a 4-dimensional vector, plus Ry times this 4-dimensional vector, plus Sx times this 4-dimensional vector, plus Sy times this 4-dimensional vector. This should have been a 1, 1, 1. And this is that star. Okay. So good. So we're going to start to learn to like casually manipulate expressions like this, and it'll be fun. Okay. So just for some practice, I want to ask you a little question. Suppose you have 2 qubits, as we're often going to have. A and B are in the joint state ket F tensor ket G. Okay, where like ket F and ket G are little 2-dimensional vectors. They're like, they describe the states of 1 qubit, and this kind of means that like you should imagine that Alice made a 1 qubit and it was in the state ket F. Bob made 1 qubit, it was in the state ket G, and then they got together and they didn't do anything, but they're like, maybe they're planning to do something jointly with these qubits, so we kind of need to know the joint state. But then we do a 1-qubit unitary. We'll call it W on A, the first qubit. You know, the question is, what's the new state? Now, there's like 2 ways to answer this question. You could sort of maybe go all out to like amplitudes, like write what are the 2 amplitudes of F, write are the 2 amplitudes of G, expand this out, you get an expression that looked like this. And then you could say, like, I know what to do. Like, I'm now doing a 1-qubit unitary W on A. So like this tree would kind of come out further and I'd do a calculation. But basically you can kind of do it another way, which is to say that, look, this is the state that would arise if like A made qubit state F in her own room and B made a qubit state G in her own room. And then what's the next thing that happens? We do this 1-qubit manipulation operation to qubit A. Like Alice could have just done that in the privacy of her own room. Like she didn't need yet to like get Bob involved. So it's kind of like, you know, it's equivalent to as though like, you know, Alice just did W on this 1-qubit state F, and then they brought them together. So because of this story, the answer is it's like W applied to F tensor G. Okay, so if you want, you can like maybe do a calculation with the amplitudes to verify this, but This is like the answer, and the way to think about it is that you can imagine just that Alice first did W on F before they brought the two qubits together. Okay, there's one more fact that I'm going to skip proving, and I shall leave it to the homework. But there's a lot of these like algebraic facts that it's good to learn once you learn about this tensor product symbol. And I'll just tell you this one and call it an exercise. You can probably prove it like as I'm lecturing. Let's say you're interested in the dot product of two states that look like this. So of F tensor G, if these are one qubit states, then this is a 2 qubit state, and P tensor Q. So again, this is maybe like a 4D vector, and this is a 4D vector, and now we're doing like the dot product of them. We know how to do the dot product of 4D vectors, but there's a formula for it. It's the dot product of F and P, that's a 2D vector dot a 2D vector, times, this is regular old multiplication of numbers, the dot product of G and Q. Okay, so that's how that works. This dot product with this is the product of the two dot products. And we might need this at some point, so I will ask you on the homework to verify this. So for example, if F and P happen to be perpendicular two-dimensional vectors, imagine F and P, two-dimensional vectors are perpendicular, then actually no matter what G and Q are, this 4D vector is perpendicular to this 4D vector. Because if F and P are perpendicular, this dot product is 0. So it doesn't matter what this dot product is, the whole product will be 0. Okay, so that's a little fact that we also might use, that yeah, if you just know that like F is perpendicular to P, you automatically know this 4D vector is perpendicular to this one.